Hi there, we're back to some more organic. I'm going to pick up where I left off yesterday looking at alkenes and alkynes. So alkenes are hydrocarbon chains that contain a double bond. Alkynes, Y-N-E, alkynes are hydrocarbon chains that contain one or more triple bonds, carbon-carbon triple bonds. Again, remember the double bonds and triple bonds are between adjacent carbons in a chain. So I left you with this homework 9 to 16, and I want to take a few minutes. Starting over here, I can see that it's an alkyne. I can see this one is an alkene. And then over here in the names, I'm seeing ines and enes, right, which are molecules with double and triple bonds. So if I start with question number 9 there, I'm seeing that I have 1, 2, 3 carbons. That makes it prop. And I've got a triple bond, which makes it propyne. Okay, so number 9 is propyne. Now, remember what we were doing yesterday was we were numbering where the ine is, or the ene, in the hydrocarbon chain. So in this case, if the triple bond here is between these two carbons, that makes it prop1-ine because it's after the first carbon. Notice that the triple bond here in propyne, it would also be prop1-ine because I can either count from this end or count from this end. If it's on this side, it just means I've turned the molecule upside down. If you could imagine flipping this molecule around, right, so that this carbon is on this side and this carbon's on this side, I'd have the SCH4C triple bond CH over here. So by switching it around, it doesn't matter where it is, it will be prop1-ine. So there's no other possibility. So when we name this molecule, right, it's going to be prop1-ine. Now, because there isn't another possibility, we often call it just propyne because there's no prop2-ines. There's only one possibility, so we would often ignore the one there, but I'm going to leave it in just rather than making it complicated. If I look down at my next molecule, number 10, I've got 1, 2, 3, 4 carbons in the chain, which makes it bute. And I have a double bond here. The double bond is either after the 1, 2 carbon, or if I count from the other side, remember I always want it to be the lowest number. If I count from this side, it becomes 1, 2. So either way, it's bute-2-ene. So if I was going to name number 10, I'm going to make it bute-2, it's ene because of the double bond. And then I also need, so I've named this much of the molecule so far. I haven't included this CH3 molecule, this methyl group, which is down here. So I'm going to count where the methyl group is. It would either be on the 1, 2, 3 carbon or the 1, 2 carbon. Remember, we always want to count from the same end for the enes and for the alkyl groups. So if I count from this end, it becomes 2-methyl bute-2-ene because the methyl group that 2 is a bit of a mess there. Let's just fix that up. 2-methyl, and then bute. Methyl bute is one word, and then -2-ene. Remember when I switch from letters to numbers or numbers to letters, I always put a dash. Again, I can see that up here, right, where I'm switching from the T to the 1 and the 1 to the E. So if I was going to draw the molecule that I'm seeing there, it's pent-1-ene. So if I was going to draw pent-1-ene, I'm seeing 5 carbons. It would help if I... 1, 2, 3, 4, 5 carbons. That makes it pent. And I've got a double bond, 1-ene. The ene is on the first carbon, and all the rest of the carbons are going to be single bonds. So now I need to add in my hydrogens. On the first carbon, right here, there's 2 bonds, so the carbon needs 2 hydrogens. CH2. This next carbon here has 1, 2 bonds on this side and 1 bond on this side. It already has 3 bonds. 3 of its valence electrons are used. It has 1 left over, so I need to put an H in here. My next one here, this carbon has a bond to carbon and a bond to carbon, so it needs 2 more bonds. So I'm going to make it CH2. The same thing here, CH2. And then my last one becomes CH3. So there's pent 1-ene, right? 5 carbons pent, ene being a double bond, 1-ene saying the double bond is on the 1 carbon. Question 12 there says ethine. You think, well, there should be a number telling me where the ine is, but it turns out if I drew eth, it's only got 2 carbons. 1 carbon, 2 carbons. Actually, I'm going to make that a bit further over because I need to give myself space here. 2 carbons, right? And now I need, for ethine, I need 1, 2, 3. There's my triple bond, which makes it an ine. And now I need to figure out how many hydrogens does each carbon need. The carbon on the left has 3 bonds, so it needs a hydrogen. The carbon on the right has 3 bonds, so it needs a hydrogen. So I need to put a hydrogen in here. And again, I'm just going to move this over a bit. I haven't given myself room to work. And I need a hydrogen on this carbon also. That becomes ethine. Now, if I move down to question 13, it's getting a little more complicated. 4-methyl-oct-3-ene. 4-methyl-oct-3-ene. Now, typically, I'm going to ignore the beginning part, and I'm just going to draw the oct-3-ene in first. Oct-3-ene. So, let me erase this here, and I'm going to draw in my oct-3-ene right here. Oct means 8. 1, 2, 3, 4, 5, 6, 7, 8 carbons. So that's my oct. And then I need a 3-ene. So after the 3rd carbon, 1, 2, 3, I need a 3-ene. I need a double bond. So I'm going to put my double bond in here to show that I've got oct-3-ene. Now that I've got that all organized, I need single bonds in for all the rest of my spots here. And I also now need to think what else was in that name. There was also a 4-methyl. So I've already drawn the oct-3-ene. Now I need a 4-methyl. Since I started counting at this end, I've got to still count again at the same end. So this was 1, 2, 3. This would be the 4 carbon right here. So on the 4 carbon, I need to put in a methyl group, a CH3 group. Now, if I go all the way back and put the rest of my hydrogens in, this first carbon has only 1 bond, so it needs 3 hydrogens, CH3. The second carbon here has only 2 bonds. It has a bond here and a bond on this side, so it needs 2 more hydrogens. The next one, this carbon has 1, 2 bonds on the right and a bond on the left, so it already has 3 electrons being used. It needs 1 more. So I'm going to put a hydrogen in here. This next carbon, notice it's already got 1, 2 bonds here, a 3rd bond down here, a 4th bond there. This carbon already is using all of its 4 electrons. It doesn't have to use any for hydrogens. So there's no hydrogens on that carbon. The next one here is going to be CH2, right, because it already has 2 bonds. This next one is going to be CH2 because it's already got 2 bonds. This one's going to be CH2 because it has 2 bonds. And then the end one down here only has 1 bond, so it needs 3 more hydrogens. It needs to be CH3. So that molecule there is number 13. It's 4-methyl-oct-3-ene. Okay, let's go down to 14. Sorry, that's 14. Let's go down to 15. So I'll draw 15 up here again. Okay, so for 15, I'm going to make this a little bit bigger so I have a little more room to work here. For 14, I've got 5-butyl non-1-ene. Okay, so let's again draw the non-1-ene first. So non means 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8. I'll put one up here. 9. So there's my 9 carbons. There's 9. I can see that I have one ene here, right? So I have to have a double bond on the one carbon. Double bond on the one carbon. And now I'm going to, before I put in the rest of my hydrogens, I'm going to say, what else do I need? Well, I've already done the non-1-ene, right? The non-1-ene is right there, and now I need to put a 5-butyl. Remember, I need to count from the same end. If this was the one carbon, it is still the one carbon. So 1, 2, 3, 4, 5. So this kind of funny looking C right here is where I'm going to add my butyl. Now, it's 5-butyl, so on the 5 carbon, butyl means 4 carbons, so it's going to be CH2 bond CH2 bond CH2 bond CH3. It doesn't really matter how I draw that in, so long as it's a straight chain coming off that 5 carbon. And then for the rest of the molecule, I need to flood it with hydrogens. So the first carbon has 2 bonds, needs 2 hydrogens. The next carbon has 3 bonds already, it needs a hydrogen. The next carbon, the next one, CH2, this one here has 3 bonds already, right? It's got a bond here, and a bond here. So it still needs another hydrogen. Oops. It needs a hydrogen because it's got to have 4 bonds. The next carbon is CH2. The next carbon is CH2. The next carbon is CH2. And the last carbon is CH3. Okay, so that becomes 5-butyl non-1-ene. Okay, so that's number 14. Okay, let's go up to number 15. 15 is hept2-ine. So, oops, I'm going to take all this away. So I've got some working space here. Okay, hept2-ine, number 15. Hept means 7 carbons. 1, 2, 3, 4, 5, 6, 7. There's hept. It's 2-ine, so I need to look at after the second carbon, I need to put my triple bond ine, my triple bond in here. Okay, so there's my triple bond. All the rest of the carbons are single bonds. And then the rest, that's it, hept2-ine. So I need to just put in the rest of my hydrogens. Notice this carbon here has 1 bond, so it needs 3 hydrogens. Notice this carbon here has 3 bonds and 1. It has 4 bonds already, no hydrogens. This carbon has 3 bonds and 1. It has 4 bonds, no hydrogen. This carbon only has 2 bonds. It needs 2 hydrogens. Same thing here. Same thing here. And this one has only 1 bond, so it needs 3 hydrogens. And that becomes hept2-ine. 7 carbons with a triple bond after the second carbon. Notice how important it is to know your prefixes, right? Your prefixes being eth, meth, oct, bute, non, hept, eth, and hex, right? Those are and again, that's all on your periodic table, so you don't even need to memorize those. I don't think it'll be long before you actually remember what they all are, but ultimately, they are the essence of organic chemistry. They're everything that you need to know for this first part of organic is based upon those 10 names that we started with last week. Number 16, let's just do that one and then we'll be done. 16 is 4-ethyl, so I'm going to clear some space up here. Okay, it's 4-ethyl hex-1-ine. So again, I'm going to do my hex-1-ine first. So hex is 6. Ine means a triple bond after the first carbon. So I'm going to do my 1, 2, 3, 4, 5, 6 carbons. Hex 1-ine means I've got a triple bond on the 1 carbon. So here's my 1 carbon, and I'm going to put my triple bond there. So I've done my hex 1-ine, and now I want to put a 4-ethyl. Again, I've got to count from the same end. So this was 1 before, so it's still 1. 1, 2, 3, 4. So on this carbon here, I need to have an ethyl group, which is a CH2, CH3. There's my ethyl group, H2, CH3. And then I need to put the rest of my hydrogens in. First carbon has 3 bonds, so it needs a hydrogen. The next carbon has 4 bonds already, so this second carbon here needs no hydrogens. The next carbon has 2 bonds, so it needs 2 hydrogens. The next carbon has 1, 2, 3 bonds, so it needs a hydrogen. The next carbon needs 2 hydrogens, and then the last carbon, as usual, needs 3 hydrogens. So that makes it 4-ethyl hex 1-ine. So as we're working through this organic unit, I'm going to keep bringing you back to these names and structures because they're such an important part of organic chemistry. All right, so I want to move on today to section 3.5. 3.5 looks at, now that we know methane, ethane, propane, butane, and we know some of the side groups, methyl butane, ethyl nonane, ethyl nonene, right? When we're naming these things, the question is, so we know what they look like in terms of chemical, in terms of carbons and hydrogens and single and double bonds. But what are these different chemicals used for, and how are they different? Well, it turns out that most of these hydrocarbons come to us in the form of crude oil. So one of the things that we are kind of famous for in this country is our Alberta oil sands, right, and all the resources. We've got so much crude oil in this country, and basically what we do is we dig into the ground areas that are known to contain crude oil. People who are prospectors spend huge amounts of time and energy trying to find places where there is crude oil buried, and when they find a supply of it buried, then we'll go and we'll start pumping it out of the ground. Then we end up with these big barrels, right? We buy it by the barrel. We end up with these big barrels of this black, smelly, thick stuff called crude oil. And it is crude, which means it's just rough, and it's oil. It's a mixture of things. Now, it turns out in there are so many of the chemicals that we need to use, but as a mixture, it's useless. I need to be able to separate the methane from the ethane, from the propane, from the butane, from the octane, from the decane. We need to separate them because each one of them has its own specific uses for us as consumers and as chemists. So as we work through this, it's important that we recognize that different alkanes are going to have different purposes. So our very small alkanes, C1 to C4, where's my pointer? There it is. Between 1 and 4 carbons, in other words, methane, ethane, propane, butane, those are typically used, they're gases at room temperature, which means for it to be a gas, it has to have boiled. And it turns out that the boiling points are below the temperature of the room. Because of that, they've already boiled. At the temperature that the room is, at even a colder temperature, they turn into a gas. And now they exist at room temperature as a gas. And we use them for heating for cooking. We use them for furnaces, for heating our homes, for hot water heaters. Larger alkanes, like C5 to C16, are often used as different type of fuels. Some of them are used as fuels for cars. Some of them are used for airplanes, and for jets and for rockets and all kinds of things. When we get to heavier carbons, heavier hydrocarbons, more carbons, 16 to 22 carbons, we can see that they are becoming thicker and thicker, right? They are often used as lubricants, right? Sometimes we burn them in oil burning furnaces, but for the most part, they're now liquids at room temperature. Some of them become solids at room temperature. You can see down here in D that some alkanes, if they have closer to 20 carbons, right, they will be waxes at room temperature, but they melt at reasonable temperatures. Like, you don't have to get them ridiculously hot to melt them, and they will turn into a liquid, and then they will burn. Some of them are used for making lipstick. They're used for making different types of cosmetics, foundation and blush, eyeliner, and they are carbon-containing materials. They're not dangerous or hazardous, and they're things that we use in our cosmetic industry. And then once we get to E here, which are larger molecules that contain 20 plus carbons, a lot of them are solids at room temperature, and we've got to get them really hot, and then at room temperature they'll turn basically into a very thick liquid or a solid. We use them for our roads. We use them for roofing on our houses, and at room temperature, like I said, it will turn into a waterproof solid. So those are all the different hydrocarbons. Now it turns out that there's a relationship between how big the hydrocarbon is and its boiling point. Notice that methane here boils at minus 164. In other words, at any temperature above minus 164 degrees, it's going to be a gas because it's already boiled. If I want to turn it to a liquid, I've got to cool it to colder than minus 164. Ethane, minus 89. Propane, butane, right? They're all gases at room temperature. Room temperature is around 25 degrees Celsius, right? So they're all gases at room temperature. Pentane, hexane, and heptane, they will all be liquids at room temperature, but they don't need to be heated too much for them to boil, right? And then octane, nonane, and decane. So you can see that each hydrocarbon has its own boiling point, and that's actually a good thing for us because we've found out a way to separate the hydrocarbon mixture, which is crude oil, based upon the temperature of the mixture. So if we heat it to different temperatures, I can cause different parts of it to boil while leaving the rest of it. So if you could imagine, if I had a mixture of pentane and hexane, both liquids, and I put them together and I shake them up in a bottle and I gave it to you and I said, how would you separate it? Well, if I warmed it to 50 degrees, right? If I warmed it to 50 degrees, the hexane would stay as a liquid, but the pentane would boil because it boils when it gets to 36 degrees. So the pentane would come off as a gas. Maybe I could collect the gas, and the hexane would stay as a liquid, and I could separate the two by getting them to a temperature between those temperatures. Getting them to a temperature between those two boiling points. And we do the same thing for all of these. So by heating our mixture up in stages, we actually are able to separate the mixture into its components. Now let me just shoot back to my note here. So in my note, right, so I'm saying the key points here, the fact that various hydrocarbons have different boiling points. Bigger molecules will have higher boiling points, and the reason why they have a higher boiling point is because bigger molecules are attracted to their neighbors. There's a chemical bond that basically holds molecules together. The bigger the molecule, the greater the hold that they have on their neighbors, and the more you have to heat them in order to make them separate or boil, turn to a gas. So large molecules have greater attraction, and because of that, again, this is right out of the textbook, you can see the larger molecules have the larger boiling points. Now, again, this is from the picture that we just looked at in the textbook that shows gases at small hydrocarbons. Liquids are still small but getting bigger. Some of the larger ones, C20 and plus, are either thick liquids or even solids. Now, we know that a lot of these things, our crude oil, comes from fossil fuels. Fossil fuels tell me two parts here. One is the word fossil, and one is the word fuel. Fossil are things that basically existed a long time ago that are now gone. And for the most part, things that are and they're fuels, right? They're things that we burn. So there are things that we burn that were here a long time ago. And what's happened is those organisms that were alive, plants and animals and whatever that was alive many years ago, they, for the most part, got buried under the ground. Some of the cases because of the movement of glaciers. And as the glaciers were moving, the glaciers worked like a snow shovel. If you can imagine how a snow shovel works, again, if this is the road here, or if this is my driveway, and here's my shovel, right, and here's the person pushing the shovel, right, as I'm pushing on that shovel, the snow that's down here, as the shovel moves forward, the snow gets flipped upside down, and the shovel keeps going this way and flips the snow upside down, and the snow keeps getting flipped up onto the shovel, and then you toss it, and then you push it a bit further, and the snow gets flipped up onto the shovel, and you toss it. Well, the glaciers did the same thing, right? The glaciers oh, worked like a shovel. And what happened was there would have been trees down here, and animals down here, and insects down here, and all kinds of stuff down here, and this huge glacier would have come along, and as it was moving along, it moved this way and flipped everything that was here upside down, so it got buried. And all this organic matter, remember organics used to be considered things that were alive, all this organic matter got buried into the ground, deep underground, by the flipping of the soil, by the glaciers, and then it decayed there. Because there's no oxygen down there, it decays and it turns into hydrocarbons. With oxygen there, it would have rotted, but with no oxygen, it turns into hydrocarbons. So we now have all this stuff that's being produced because of decaying biological matter, right, deep in the earth, and it turns into this crude oil, which ultimately is this mixture. So now the good thing for us is that the mixture contains all these different components that have different boiling points, and ultimately what we're going to do is we're going to heat the mixture of hydrocarbons at the very bottom of a fractionation tower here, and as we pump the crude oil in here at high temperature, most of it has boiled already. Some of it is still a liquid, and it will basically drip down to the bottom here, and it will escape down here. That's called bitumen. All right, bitumen. Again, we hear bitumen sometimes in the news, and it's the largest hydrocarbons in the mixture. And then what happens is, as the gas gets carried up the column here, it's cooler in this chamber, a little bit cooler in this chamber, a little bit cooler in this chamber. And like I was saying, we separate the mixture because every time it cools a little bit, some of the hydrocarbons will now condense. They will turn from a gas into a liquid, and then whatever condenses, we will collect it. So the higher we go up, the smaller the hydrocarbons. So at the top here, I'm seeing 5 to 12 hydrocarbons in length, 12 to 15 carbons, 15 to 18, 18 plus, 20 plus, right? And then these things here, these become gasoline. This becomes naphtha that we often use for making plastics and different types of chemicals that we use in our society. This is kerosene, which can be used as a fuel, and then heavy fuels like diesel down here with large hydrocarbon chains. So we're kind of lucky that we can separate our mixture based upon the size of their hydrocarbons. Now, before I leave, I'm not sure if I can show a YouTube video here, but I'm going to try and add it to my video. If I get kicked out, I'm going to stop there. That's the end of 3.6. And I'm going to leave you with the homework in the textbook. Again, there's a bit of an article here that you've already done when you did the STSC for organic chemistry for Unit 2, which you've all done. We've already read a little bit about organic chemistry and Canada's oil supplies. I'm going to leave you with the homework here on page 110 of our textbook, questions 1 to 9. Right, questions 1 to 9 on page 110. Now, like I said, I'm going to try and see if I can't add a video clip from YouTube into my video here, but it may kick me out. So if it does, I will finish there. If not, I will leave some links for you to watch the video, but I'm kind of hoping I can do this. Let me see what I can do.
In this video, you will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics. However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas. They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required, a higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule. Let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapour form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still high, some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column. The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapour, and eventually the vapours get too cool, condense, and are collected as liquids in the trays. Small molecules have low boiling points, and so condense much higher in the column, where the temperature is cooler still. As you can see, hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars, naphtha, used in the manufacture of chemicals, kerosene as aircraft fuel, diesel oil, used as fuels for vans, cars and lorries, and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling point. You should understand that small chain molecules are collected at the top of the column since they have lower boiling points, and larger chain molecules are collected further down the column as these have higher boiling points.
Okay, so you can see how we are using the fractional distillation, right, which is distillation, which is heating chemicals up that have different boiling points and then separating them into fractions, into parts of the whole, right? So the whole is the black crude oil that goes in, and then the fractions are the light hydrocarbons, the medium ones, the heavier ones, the heavier ones, the heaviest ones. All of these are fractions, including the very light ones that come out of the top. These are all fractions of the whole, and they basically make up the crude